In this video, we're going to do two more examples to finish up our rational inequalities. So the first one is we're going to solve and graph the solution set for this rational inequality. So it's already in the good form. We have 0 on one side. So remember what we have to do first is find the boundary points to plot on this solution real line. So the boundary points are obtained by setting the numerator to 0 and solving, setting the denominator equal to 0 and solving. And that's how you get the boundary points. So BP's boundary points, and maybe I'll write NUM for numerator. And we get x squared plus 4x plus 3, set that equal to 0. And then we'll factor. So we'd have an x and an x and a plus because they multiplies to 3, the two numbers, and they add to 4. So that would be a 3 and a 1. So setting each of those factors to 0 would give us boundary points of -3 and a -1. Maybe I'll write them over here. And then for the denominator, that'll be pretty trivial. Denominator. X minus 5 equals 0 means x equals 5. So that would be our third and final boundary point. So let's plot those. We'll put -3 here, -1 there, and 5 we'll put about there. All right, well, do we know if these are going to be filled in or are they going to stay open circles? Well, we actually do know if we look ahead a little bit. The only one, since this is greater than or equal, we might think we want to fill all of them in, but one of them will cause a problem, that denominator. In no way can x equal 5 be a solution. So that is going to stay an open circle. But because it's greater than or equal, everything else will get filled in. You're allowed to plug in, if you plug in -3, you're going to get a 0, and 0 is greater than or equal to 0. If you plug in a -1, you're going to get a 0. 0 is greater than or equal to 0. But if you plug in a 5, you're going to get something divided by 0, which is not even a number. It could not possibly be in the solution set. Okay, let's pick our test points. Pick a test point over here, maybe -4. In between here, maybe -2. And in here, we can get a 0. And over here, we can get 6. And now I need to compute, and I didn't write down, but we're going to call this the function f of x that I've circled here. So f of -4 will be let's see, -4 squared is 16, minus 16, because 4 times -4 is -16, plus 3. All over, -4 minus 5 is -9. So we get 0.3 over -9. All we care about is that it's less than 0. If it's less than 0, this inequality won't be satisfied. If you plug in -4, you're going to get something less than 0, which means anything in this whole region from -infinity up to, but not including -3, will fail. So I'm just going to put an X mark there saying I checked it, but I'm not shading it. Now let's look at f of -2. f of -2. That's our -2 is our test point. So we'll get 2 squared, which is 4, plus 4 times 2 is 8, plus 3, all over -2 minus 5, which is -7 in the denominator, and this is a positive number upstairs. So let me double check that. -2 would be 4 minus 8 plus 3. Okay, so that's going to be, what did I do wrong? 4, oh, it's not plus 8, it's minus 8. So negative 7 in the denominator, 4 and 3 is 7. 7 minus 8 is negative 1, so we get positive 1/7, which is bigger than 0. And that's good. That's a region, because we want it greater than or equal to 0. We'll shade that entire region. And f of, I'm going to move over to the left here, and go f of 0. That should be easy to compute. If x is a 0, we get negative 3/5. Negative 3/5 does not satisfy this because it's negative, so we do not shade this region. And then we go to f of 6. And we will get 36, because 6 squared, plus 4 times 6 is 24, plus 3, all over 6 minus 5, which is 1, and clearly that's a positive number. I'll just put greater than 0. And that's what we want. So we'll shade this last region as well. Infinity there, negative infinity here. So this is the graphed solution. And written in interval form, we would say negative 3 to negative 1 in square brackets, union with this interval, which would be open bracket, 5 to infinity. So that's the combined solution, two different ways of saying the solution. All right, we have one more example. A little different than the others we've done, but it'll probably be easier than the one we just did. The problem is that this is not our f of x, because we don't have 0 on one side. We need 0 all by itself. So we need to do some massaging using arithmetic or algebra. 2x over x plus 1. Let's subtract the 1 from both sides to get a 0 on this side. Minus 1, which I'll write like 1 over 1 for now, greater than 0. All we need to do is combine these into one fraction. Just get a common denominator, which means, what do we have to do? Multiply top and bottom by x plus 1. So that just means that x plus 1 over x plus 1 is equal to 1. So that's going to give us 2x minus x plus 1 over x plus 1. Now I'm hoping you caught my mistake so far. This minus, it's minus the whole thing, so I have to have parentheses around this x plus 1. This will end up being negative x minus 1. So let's see what we get. 2x minus x is x, and then the negative 1, minus 1, all over x plus 1. Oh, that's pretty easy then. This all turns into, this is equivalent to saying x minus 1 over x plus 1 greater than 0. So this is going to be our f of x. This that I just circled. So once again, all we did is subtract 1 from both sides, get a common denominator, and write it as one fraction, one rational expression. So how long does it take us to figure out what the two boundary points are? Shouldn't take more than a second or so. The top would be 0 if x is a 1. The bottom would be 0 if x is a negative 1. And there's no question about as to whether we shade these or not. We're going to leave them open because this is a strict greater than. So all we need to do is 3 test points and shade, and we'll be just about done. So for test points, let's use -2, 0, and 3. One in this region, one in this region, one in that region. And now let's evaluate the function at each one of those test points. Okay, -2. Plug in a -2, you're going to get a -3 over -1, which is 3, which is bigger than 0. I'll go ahead and shade it. Let's see, yeah, because we're looking for bigger than 0. That is bigger than 0. All right, now let's plug in a 0. A 0 would give us -1 over 1. That's less than 0. And the plugging in a 3 would give us a 2 over x3 plus 1 is 4 for 1/2. That's greater than 0. Greater than 0 is what we want, so we shade it. So here is half the solution. That's the graphed solution. And maybe I'll write the solution using interval form right above it. So I just need to write the interval for this, union with the interval for this. So negative infinity to negative 1, union 1 to infinity. Simple as that.